This is the second supplemental video for Chapter 11, focusing on the distribution of the sample mean. The sample mean, which we can denote with the notation x bar, is a random variable. Why is this? Well, consider a random variable x that in the population has a mean mu and a variance sigma squared. If I select a random sample of size n from the population, I can't know in advance which of the individuals are going to be chosen or what the sample mean will be. But once I select the sample, I'll be able to calculate the sample mean by adding up all of the values that are from the selected individuals from the population and dividing by n. Recall that the distribution of the sample mean is called its sampling distribution, and we're going to learn about appropriate probability models for the sampling distribution in this video. First, we'll think about the mean and the variance of the sampling distribution for the mean. So if we look at the formula that we use to calculate the sample mean, we can see that it's a linear combination of the values, the random values that we're selecting from the population. And since each of those is selected randomly from a population with the same mean, the mean of the sample mean, so the mean of the sampling distribution for the sample mean, can be shown to be equal to the mean of the population, mu. And similarly, the variance of the sample mean, which is then the variance of the sampling distribution, can be shown to be the population variance, sigma squared, divided by n. Recall that the standard error is what we call the standard deviation of the sampling distribution. So that's just a special name for the standard deviation for the sampling distribution. And for the sample mean, the standard error is given by the formula. Standard error equals the square root of the variance of the sample mean, which gives us a standard error of sigma over the square root of n. And I did introduce that formula in class earlier in the semester, but without any sort of rationale for it. So this is sort of where it came from. Under some conditions, the sampling distribution for the mean is approximately normal. The first condition in which this will be true is if the distribution of the random variable x is normal in the population that we're sampling from, then the sampling distribution for the mean will be normal for any sample size. The second condition is that if the sample size is big enough, the sampling distribution is approximately normal, even if the distribution of the random variable x is not normal in the population. This is a result of the central limit theorem. Now, just to kind of reinforce the difference between a standard deviation and a standard error, I want to talk about that for just a minute. Standard deviation measures variability among individuals, either in the population, if we're calculating a population standard deviation, or in the sample, if we're calculating the sample standard deviation, but always measures variability among individuals. Can interpret the standard deviation as a measure of how far individual values typically deviate from the average. And the standard deviation is useful for deciding if an individual is unusual or not. In comparison, the standard error measures variability among statistics that are calculated from different random samples. We can interpret the standard error as telling us how far a sample statistic will typically deviate from the population parameter that we're using it to estimate. And standard error is useful for deciding if a sample, in particular a sample statistic, is unusual. One way that we can measure how unusual a value is by using something called the z-score. The z-score measures how many standard deviations a value is from the mean. When the z-score is positive, it indicates that the value is greater than the mean. And when it's negative, it indicates that the value is less than the mean. Values that are more standard deviations away from the mean are more unusual. So z-scores that are farther from 0 would indicate more unusual values. In a normal distribution with a mean of 100 and a standard deviation of 8, how many standard deviations from the mean is 90, and how many standard deviations from the mean is 116? We're going to calculate the z-scores for each of these values. The z-score for 90, you can see, is negative 1.25, which tells us that 90 is 1.25 standard deviations less than the mean. Calculating the z-score for 116 in this distribution gives us a z-score of 2. So 116 is 2 standard deviations greater than the mean. And the 116 would be a more unusual value in this situation. More standard deviations away from the mean. I'm going to talk now about a special type of normal distribution, which is called the standard normal or Z distribution. The normal distribution that has mean 0 and standard deviation 1 is called the standard normal distribution. It's the only member of that family of distributions that has a special name. If x is a random variable that has a normal distribution with mean mu and standard deviation sigma, then if we calculate the z-scores for x, the random variable that is that z-score will have a standard normal or a z distribution, and this is why the standard normal is called the z distribution. Now this is a very useful property. It was especially useful before we had computers that could calculate percentiles and quantiles of normal distributions very, very quickly. We used to have to use tables, and as you can imagine, we couldn't have had a table for every possible combination of mean and standard deviation. So working with the standard normal table was a way to need only one table to calculate probabilities and percentiles and quantiles for any normal distribution, and we'll see how to do that in just a second. So if we wanted to use z-scores to calculate normal probabilities, just to look at how we can do that, first of all, I'm going to use the method that we've seen already in Chapter 11 to find the probability that a random variable x falls between 90 and 116 in a normal distribution with a mean of 100 and standard deviation of 8. So I can do this with the p-norm function. First, I take the probability that the random variable is less than 116. That's what that p-norm 116, comma, mean standard deviation is giving me. Then I subtract off the probability that's less than 90 to get the probability that's in the middle. And I can see that that probability comes out to 0.87 approximately. Now remember that we just calculated the z-scores for 90 and 116 in this distribution in the last example that we did. And they were negative 1.25 for 90 and 2 for 116. So if I find the probability that a normal random variable in a standard normal with mean 0 and standard deviation 1 falls between negative 1.25 and 2, I can do that also with R. Now I'm using the z-scores, 2 and negative 1.25, and I am using the mean and standard deviation, 0 and 1, for the standard normal or z distribution. And we can see that we get the same probability here. So essentially, this happens because all normal distributions, if we want to know the area between two values in a normal distribution, the only thing we need to know is how many standard deviations those values are from the mean. Now, if I want to find the middle 95% of a normal distribution, I can start by finding the middle 95% of a standard normal distribution using the quantile function to find the 2.5 and 97.5 quantiles of the standard normal with mean 0, standard deviation 1. I can see that in a standard normal, the middle 95% of the distribution is between negative 1.96 approximately and positive 1.96. Now, if I find the values that are 1.96 standard deviations below and above the mean in a normal distribution with a mean of 100 and a standard deviation of 8, I take the mean and subtract 1.96 times 8, gives me 84.32, and then take the mean 100 and add 1.96 times the standard deviation of 8, gives me 115.68. And what we can see is that if I used R instead to find the middle 95% of the normal distribution with mean 100 and standard deviation 8, I get those same values. So again, we can work with the standard normal and use it to find percentiles and quantiles for any normal distribution. Okay, so now let's apply this to the sampling distribution. Suppose a random variable x has mean mu and standard deviation sigma. If conditions are met, and we talked about those conditions a little while ago, the sample mean will have a normal distribution, or approximately normal, with the mean of the sampling distribution equal to mu and the standard error equal to sigma over the square root of n. Since that's a normal distribution, that means that if we calculate the z-score, taking x bar minus the mean of its sampling distribution, mu, and dividing by the standard error, that z random variable is going to have a standard normal distribution. This is useful because it means we can use the normal distribution to calculate C% confidence intervals. If the sampling distribution is approximately normal and we know the population standard deviation, then we can find the value z star such that C% of the standard normal distribution is between negative z star and positive z star. If we were to take a sample of size n, then we know that there's a C% chance that the sample mean will be within z star standard errors of the population mean. And so a reasonable way to make a C% confidence interval based on a sample mean would be to use this formula to take the sample mean plus and minus z star times the standard error. And that could give us a confidence interval for the mean using a normal distribution. And this will work perfectly as long as we know the population standard deviation sigma. In reality, though, if we didn't collect data from the whole population, we would not know the population standard deviation. And so we can't generally use this formula. We're going to need to make an adjustment in order to be able to estimate the standard error. When we don't know the population standard deviation, we can't use it to calculate the standard error. Now, we know that if we did know the population standard deviation, this z would have a standard normal distribution. Since sigma is unknown, we're going to need to estimate it with the standard deviation calculated from the sample, which we call S. But because we're estimating an extra value, this is going to introduce more variability into this quantity. So it turns out that when we calculate the sample mean minus the population mean divided by S over the square root of n, this has more variation than a standard normal distribution. It has a distribution that's called a t distribution. Now, a t distribution is somewhat similar to a normal distribution, standard normal distribution that is, in that it is centered at 0 always, and unimodal and symmetric. The way that it's different is that there's more area in the tails compared to a normal distribution. And how much more area there is in the tails depends on the degrees of freedom, which is how we differentiate between different t distributions in the family. The way that we calculate the degrees of freedom is by taking the sample size minus 1. Now, as the degrees of freedom get larger and larger, the t distribution gets closer and closer to a standard normal distribution. And this is because with a larger sample size, we have a more reliable and consistent estimate of the population standard deviation. And so we get closer to that situation where we know the population standard deviation, which would put us in a z distribution. So when we don't know the population standard deviation, we use a t distribution to make a confidence interval. To make a c% confidence interval with the t distribution, we start by finding the t star value such that c% of a t distribution with n minus 1 degrees of freedom is between negative t star and positive t star. Then, based on the sample mean, we can calculate a c% confidence interval by using the sample mean plus or minus t star times our estimate of the standard error, s over the square root of n. We'll do an example. Suppose we want to make a 90% confidence interval for the mean height among 14-year-old girls. We're going to start by taking a sample and summarizing the data in that sample. In the sample, the mean height is 1.514451 meters, and the standard deviation is about 0.0707. And here we can see a histogram of the data in the sample. There are n equals 32 girls, ages 14, in the sample. We've got a reasonably symmetric, slightly skewed distribution in the sample. Now we're going to find the t star values that are going to cut off the middle 90% of the t distribution. So I'm going to use the qt function to find the quantile, q for quantile, t for t distribution. And then to cut off the middle 90%, I need the 5% quantile and the 95% quantile. So there'll be 90% in between there. And for a t, I need to specify the degrees of freedom. The degrees of freedom, remember, are n minus 1, so that's why I have 31 degrees of freedom. And we can see the t star value here is 1.6955. Now when I want to make my confidence interval, I take my sample mean and I add and subtract my t star value, which I rounded to 1.696, times the standard deviation from my sample, 0.071, divided by the square root of the sample size, 32. And this gives us a confidence interval that goes from 1.493 to 1.535 meters. And finally, I will interpret my confidence interval. I'm 95% confident that the mean height in the population of all 14-year-old girls is between 1.493 and 1.535 meters. Now, I just want to compare the confidence interval we made using this t-distribution method to what might have happened if we had used our old resampling distribution or bootstrap method. So remember that our 90% confidence interval based on the t-distribution went from 1.493 up to 1.535. Using the bootstrap resampling distribution method, I used the do function to do 1,000 resamplings and calculate the mean height from every resampling of the original data. Then I calculated a confidence interval with a 90% confidence level, level equals 0.9, and it gave me a lower limit of 1.494 and an upper limit of 1.535 if I round to 3 decimal places. So this is just to show us that although they don't come out to be exactly the same, we have very, very similar confidence intervals based on the two methods, which is a good thing because if we have two good methods for doing estimation, we'd like to see that they give us very consistent results, and in fact that was true here. So before Thursday's class, remember that you should complete the practice exercises that are in the course materials. Should also get started on the homework if you haven't already, so that if you have any questions, you can ask them. And then come to the live meeting time on Thursday at 8:45 with your questions. I look forward to seeing you then. Thanks.